my first screen I'm going to share is the Desmos screen. So I'll go back to Google Classroom here. And if I go to, where is it? There we go. Okay, so if you type in Desmos, you'll come to probably this search here. And so Desmos is an online graphing calculator. So you click on that, it loads up. I'm gonna turn off my camera too. Not that I'm embarrassed to see myself, but I'm pretty embarrassing looking. And I'm gonna type in an equation here so you can sort of see how this works. So you just go into the box and you type in something like y equals x to the power. I use this little hat here, to the power of 2. And so you get your parabola. You guys have seen those. And if I wanted to graph another function, I could do like y equals x raised to the power of 2. So that would be, oopsie. Is that gonna, oh, I just did this, right. How about this? 2 to the power of x. There we go. And you can see you get a exponential function. And you could graph all kinds of functions, like y equals x to the power of 3, and then plus x minus 2, so polynomial type function. And you can just keep doing this, all the functions you could think of. And so I'm going to use this for graphing trigonometric functions and seeing some of the patterns that we notice here. So I'm going to graph our first trig function that we did in yesterday's video. And if you didn't get a chance to see yesterday's video, this might be a little bit disjointed here, but I would encourage you to watch that tonight. So the first function we wanted to look at was y equals sine of x. And we usually use theta for the angle, but for this program, you'll be using the x as your variable. Okay, so there's what a sine curve kind of looks like, but the axis is a bit out here, and so I'm going to go up to this little wrench here, and I'm going to change this to my x values. Let's go from maybe let's work in radians here. So let's work at negative pi, and then going all the way to 2 pi. And you actually just type in the letters pi, and the little pi symbol pops up. And I'm going to change my y-axis to -1 and 1. And my step here is what each little dash will show. So right now you can see 1, 2, 3 on the graph, but I'm going to make it pi divided by 2, which is 90 degrees here. Let's close the wrench up, and you can see sort of one of the sort of pattern here of going up and then down, and that's your typical sine graph. And I go to 0, get rid of that. Now what you can see is what we call one period of the function. So this would be one cycle or one period of the function. And there's some words we use like amplitude and the period and stuff, and we'll talk about those here. And now if I graph on the same grid, I just sort of compare these functions, y equals cos of x. I get this graph, and you can see it's very similar looking, but purple graph's a little bit almost like it's been moved to the left. It's almost like the red graph and moved left a certain number of units. And so you might remember chapter 1, translations, moving things left and right. And that's basically, you can write a sine graph and a cos graph the same here. In fact, let's do that to show you that. I'm going to kind of jump ahead in the lesson here, but if you took the red graph, the sine graph, let's do sine, and I'm going to put brackets here, and you're going to move the red graph to the left, then you would want to do something to the x values. So what I'm going to do is I'm going to move all of these values left by pi over 2, because you can see that they moved, the high part is at pi over 2. So I'm going to go left, and I might have to remember, if you're going to go left, you have to go plus pi divided by 2. And see how when I did that, I'm going to get rid of that again. See the purple graph? And then as soon as I put a 2 in, now the black graph goes over top of it. And I'm going to close my brackets. And I get this function. Now, if you wanted to, if you could, if you click over here on this circle, it actually turns that graph off, but keeps the equation here. So if I turn that off, you can see the purple graph reappears. And when I press that again, the black graph goes right over top of it. So as we go through this chapter, if you're having a hard time graphing a function, I think this program is really useful for you to sort of test your theories and ideas on what the graphs look like. So let's go back to the Google Classroom, or sorry, the OneNote here. And so I'm going to switch, let's see here, switch to OneNote. And we can sort of see, this is the notes that I did from yesterday's video here. So you guys can watch that obviously on your own time. But we'll just continue on with where we got to here. So let's take a look at y equals sine of x, sine of theta. And there's two ways of looking at this. One is the unit circle. And I think for many of you guys, this is probably the best way to start thinking about it. And then we can move into sort of looking at it in terms of a point moving along a curve here. So if this is pi over 2, this is 0, this is pi, this is 3 pi over 2, and we go back to 2 pi. And so if we look at the coordinates here, this was 1, 0 on the unit circle. This was 0, 1. This was negative 1, 0. And this down here was 0, negative 1. And I'm going to redo a little bit of yesterday's lesson just to kind of build on what we talked about yesterday. But I think just for those students who maybe didn't get a chance to see it, it would be useful to do that. So I'm going to put a look at theta and then a value of sine theta. And I'm going to work in radians here. So hopefully we're sort of getting comfortable with radians. And I'm going to put theta at 0, pi over 2, pi, 3 pi over 2. And let's go down to 2 pi. And what we should notice about 2 pi is let me see here, I get for this bar. Okay, there we go. So, so what I'm going to do here is I'm going to take a look at 0 and 2 pi. And what I should notice is these values should be the same because they're really at the same place on the graph here. So remember that sine is defined to be y over r. And as you move from, say, 0 to pi over 2, what's happening to the y values here? Well, the y values are going from 0 to 1, so they're getting larger. Now, in fact, the sine of 0, if someone said, what is the sine of 0? Well, it'd be the y value, which is 0, over the radius of 1, which is 0. So this should be 0 here. And if you look at sine of pi over 2, well, pi over 2, you're at the top here, so your y value is now 1. So the sine of 0, I said. So the sine of pi over 2, you would have a y value of 1 divided by a radius of 1, which is 1. Sine of pi has a y value of 0 over 1 is equal to 0. And sine of 3 pi over 2 would be negative 1 over 1, which is negative 1. And then the sine of 2 pi should be the same as sine of 0. You're back at the beginning again. And so you kind of go from these values 0, 1, negative 1, 0, 1. Okay. And if you, can I show that here? Actually, if, Briley, I'm going to get you to turn your mic off and just answer a quick question here, okay?
Yeah.
Okay. So my question is, if I, has the screen changed for you at all?
No.
Okay. So, okay. Thank you. I can't do that. Okay. So, so when we look at, share this. Yeah, there we go. Okay. So if I was to graph these, and I'm going to graph them in a slightly different way, I'm going to draw a graph like this. And I'm going to divide this into 4 equal sections. And each one of these sections is supposed to represent this graph up here. So I'm going to start at 0 being kind of over there, pi over 2 being here, pi being here, 3 pi over 2, and 2 pi. And what I notice from the red values, I kind of go from 0, 1, -1, 0, 1. So if I plot those points, I'm at 0, I'm at 1, I'm at 0, I'm at -1, and I'm at 0. And of course, if you think about rotating, let's get rid of that red line on the graph here. If I was to rotate from here to here, that there, the y values should be getting larger and larger, and they are. They're getting bigger and bigger and bigger. And of course, as you go from pi over 2 down to here, they're getting smaller now, so they're getting smaller. And of course, here the y values are getting even smaller. They're getting further down on the graph. And then as you get to the bottom, you start to come back up again, and you can see you're back where you began here. So after 2 pi, what do you think would happen here? So let's say you went past 2 pi on the graph. You kind of just kept drawing the picture. Well, you should just repeat the pattern here. So just kind of go up, 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 and then start going down again, and you get this repeating pattern. And of course, if you were to start at 0 and go backwards, you would go down on this side, and it would eventually repeat the pattern here. So this pattern, where we say it's one turn of the wheel, we call that a period. So that's a period of the function. And then the height of the function from the highest point to the middle, we call that the amplitude of the function. So that's our amplitude here. So I'm just gonna work with sine right now. I'll bring cos into it in a little bit here. And I just want to introduce a couple different changes here. And what you're gonna find is these changes are really related to transformations. So if you think back to the very first unit we did, where we stretched graphs, we vertically expanded them, we compressed them and stuff. It's actually all the same things you learned there. There's just some different names for it. And the main reason for that is the area we see this studied in is mostly in areas like physics and engineering, computer science. So, so let's take a look at some transformations. So a really kind of simple one here would be y equals 2 sine theta. Y equals negative sine theta, and y equals negative 3 sine theta. Okay, and so I'm going to ask you guys to write those three equations down, because I'm going to flip back to the Desmos screen to talk about what they would do there. So if you just take a second to write those down before I change the screen. Okay, hang on. Let's go switch my screen. Okay, so I'm going to go back to Desmos here. Okay, so I'm going to get rid of these other two functions I kind of added in here. And there we go. So there's our sine graph here. So the first one we're going to do is y equals 2 sine theta. So basically we're putting a 2 in front of that value, so sine. And we're curious, how does that affect the graph here? Now, back in chapter 1, putting a number in front of a function causes what was known as a vertical translation. And so this should cause the graph to get stretched, actually. So let's just see what that looks like. And we can see definitely it does do that. But it's kind of hard to see exactly where it goes there. So I'm going to change the wrench, and I'm going to just make my y values a bit more extreme. So -4 to 4. Okay, so if I look at the two graphs, they're both sine graphs. They both seem to start on the middle and kind of go up, 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 down, and then kind of repeat the pattern. They both have the same period. They both start at 0 and end at 2 pi, so it didn't affect the period by doing that. But putting a 2 there did cause the graph to get higher here. So it didn't change period, but it did change the amplitude. So if you go from the middle of the graph, so I think I can draw on this. Let's see here. Yeah. So if you look at this value, and you go from 0 to 2, we would say the amplitude equals 2. And even if you go from here to here, the amplitude is still 2 units. Whereas before it was only 1 unit from there to there. So by putting a 2 in front, you make things obviously bigger in the vertical direction. But what we want to kind of note here is that this changes the amplitude of the function. The next equation we entered was where we had. I'm just going to stop that. There we go. So my second graph, I think we said, was y equals negative sine. And then if we think back to chapter 1, putting a negative in front of the function should reflect it across one of the axes. So if you put a negative in front of the function, it should reflect it across the x-axis. So we should still kind of get what looks like a sine graph, but you can see it's been flipped here. So instead of going up, and then down, it actually goes down and then back up again, and everything flips around. But notice that when we look at the amplitude here, the amplitude from here, I'll erase the old notes here. So if we look at the, where's my stamp draw? If I look at this distance here, oopsie. Okay, I'm having a technical problem. There we go. If you notice this distance here, well, that's very pretty. That's 1, and the distance from here to here is also 1, and then the distance from here is 1, and the distance from here is also 1. So putting a negative 1 in front of it doesn't change the amplitude, but it does reflect it across the x-axis. And then, of course, if we do a let's switch that function off, and now we do our last function, and that was y equals negative 3 sine of x. So we should get a vertical expansion, but also a reflection. So we kind of get both things occurring here. So the sine graph has been flipped upside down again. But now, if we look at the distance from the midline to the highest point, then getting rid of this here, we could see that that this distance is. I'll get rid of all the old functions. Oopsie. So they're sort of comparing the two of them. And so if I look at the old function, this distance here was 1, but now it's 3, and it's 3 here. So that's the same as that. And of course, that 1 is the same as that one. So we notice the graph's flipped and also vertically expanded. So we would say that 2 things have happened here. It's been flipped and it's been vertically expanded. So let's switch our equations now. Let's go to cosine. And I'm going to stay on this screen here, but maybe you could write this in your notes. Let's write cos y equals cos of x. See, cos of x. We get that graph there. I'm going to turn that off, and I'm going to graph. Let's type this in first before we type it. Let's just type 2 cos of x, and down here we'll do. Let's go negative 5 cos of x. So before we show you what these graphs look like, I'd like you to just do a little sketch on your own to see if you can sort of see what they would look like if we were to draw them. Okay, so the 2 here in the second equation, 2 cos x, should cause some kind of vertical expansion. But maybe more importantly, what do you think the amplitude of that function would be? Like, imagine that we just gave you that equation. You didn't have to draw it. We just said, what's the amplitude? What do you think the height is from the middle to the highest point or to the lowest point? Well, if we graph it, we should see that it does sort of make things look taller. And now we're at 2 and -2. So the highest point is 2 and -2. And we tend to refer these as these heights here as maximums or minimums, which if you remember from grade 11, a maximum is sort of the highest value possible. So this would be a maximum of 2, and this would be a minimum of -2 down here. And if we go to the other graph, we look at what it would look like, we can see that see, turn this annotation thing off. It's actually beyond the range of what I can see here, so I could change my range. Maybe go from -5 to 5, and then close that feature down. And I can definitely see that the amplitude is 5 now, but the graph has been flipped. So let's go back to our Google, sorry, our OneNote here, and make some notes on that then, okay? Oh, seriously. Let's try that one more time. There we go. Okay. So, so if we take a look at this, we could say that y equals sine x could be changed, and y equals cos x could be changed. And I'm just going to introduce maybe three different variables today. Y is equal to a sine bx plus d, and y equals a cos bx plus d. So all we've looked at right now is the a value, the number that comes in front of the function. And so if a is, actually let's use if the absolute value of a is bigger than 1, then we get this vertical expansion. But more importantly for this unit, the absolute value of a equals the amplitude. And I'm going to show you why that's more important than knowing this, because that's what we learned in chapter 1. But I think if you know the second part of it, this part right here, you're going to find that much more useful to graphing these functions here. Okay, but I guess if you said the absolute value of a is less than 1, then you get a vertical compression. And if a is less than 0, we reflect on the x-axis. But I actually think of it more as just flipping. I just flip the sign, which sounds offensive, but we'll talk about that. So here's an example of what I mean by this sort of new way of thinking about how to graph it here. So let's say someone said, well, graph y equals -4 sine of x. Okay. Well, if someone asked me to graph that, or just sort of know what the shape looked like, the first thing I might want to do is find the amplitude. So what do you think the amplitude would be for this question? Well, notice that the a value is -4 here, so we do have a reflection. But because it's -4, sorry, I close it there. Since it's -4, we know that the actual amplitude should be 4. So up here I'm going to write 4. Down here I'm going to write -4. And what I'm going to do is I'm going to draw my sine graph, but I'm going to try to remember that, is it opening like the normal sine graph, or is it a flipped sine graph? So because this is negative, it's been flipped. So I put a point on the midline, and normally sine goes up, 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 but this is going to go down first. So it's going to go from a midpoint to a low point to a midpoint to a high point to a midpoint. So the graph should look something like that kind of thing. And then these would be 4s, -4s. And then I didn't change the period at all here, so this would still be pi, 2 pi, pi over 2 and 3 pi over 2. And you can confirm any one of these points. You probably just get used to it, but I say you confirmed it, and someone said, well, what's the sine of pi over 2? So what's the sine of pi over 2? Well, the sine of pi over 2, going up here, the sine of pi over 2 was 1, right? So we know the sine of pi over 2 is 1. So what would negative 4 times the sine of pi over 2 equal? Well, we know the sine of pi over 2 is 1, so this must equal negative 4. And you can see that right there. This confirmation way, though, it takes a long time to sort of test. What I would say is get used to maybe which way the graph kind of opens. Let's try one with cosine here, okay? So why don't you guys see if you can sketch this one? So y equals negative 3 cos of theta. Notice I switch between x's and thetas here. It just means an angle. Just what is the angle? So find your amplitude and then sketch that. Okay, so my a value is negative 3, and then the absolute value of a is the amplitude. So the absolute value of negative 3 should be 3, so it's 3. But what I would do is I would just put your dash and dash. Usually you have a high point and a low point and a midpoint. And then you're always going to have 4 quadrants on the graph. So I just draw four boxes here. And I don't really, I don't even put numbers on here. I would just sketch these and think, well, it's a cos graph. Cos always starts, high up and then goes down and back. What we've done here, though, is we have a negative in front. So really that's going to cause the graph to flip. So I'm going to start at a low point, go to a midpoint, go to a high point, go to a midpoint, go to a low point. So it kind of looks something like that. And then I'm going to put my numbers in here. So I know my amplitude is 3. So from the middle to the highest point must be 3. And then that must be negative 3. And my period is still 2 pi. So these must be each pi over 2. And it would look something like that. Okay, so that's our a value. So I'm going to skip to the d value now, and let's just take a look at this. Let's say you had y equals negative 3 cos of theta, so the one we just did, and let's say I put in a plus 2 on the end. Thinking back to chapter 1, how would that move it if you had this? You're looking at this picture, and someone said that's a function, and you now go plus 2 on the end of that. So it's kind of like f of x plus 2. So you increased it by 2. Well, according to the last chapter, that would be a vertical translation up 2. So how would we do that? Well, let's go back to our Desmos here, and we'll graph a couple functions like that. So let's go y equals I think we said y equals negative 3 cos x. I'm going to get rid of these other graphs here. So that's the one we just drew, the negative 3 cos x. And let's say you typed in y equals negative 3 cos x, but then you just add a 3 on a 2, I think it was 2 on the end, actually, maybe we did. So there's your purple graph. So you got this movement up here. Now notice there's a little bit of a difference between the two graphs in terms of where the midline is now. So if you look at the red graph, the middle line here, it's at 0. So that's the middle line for the red graph. But where's the midline of the purple graph? Where's the sort of middle place here? Well, it looks like it's also been moved up too. So it looks to me like this is the middle line for the purple graph. And that now has an amplitude of 3 that way. So that's 3. And from this side down here, that's also three units there. So this 2 on the end tells us actually where the midline is. That's actually quite helpful. So why don't you guys try this question? Just try this one here. I'll start fresher. So let's go y equals cos. Let's do sine. Y equals 2 sine x. So there's y equals 2 sine x. Let's just close these guys down for a second. Okay. And let's say you said y equals 2 sine x minus 5. So you're not gonna graph. I just don't want to type it in yet, but you're gonna graph y equals 2 sine x minus 5. So where do you think the midline would be on that graph? Let's try that. So y equals 2 sine x, and now we're gonna go minus 5. And once again, it's hard to see that, so you might need to readjust your screen, or if you were doing this on your own. And so we'd say, well, instead of -5, let's go to -7, and we'll keep this at maybe 2 or something like that. There we go. So we can see the black graph is the original graph, and the red graph is the transform graph. And so we can see that it's moved down 5. And once again, where is the midline here? Well, in the first graph, it was at 0 right there. But on the red graph, it's at 5, or sorry, -5. So you can see that number there tells you exactly where the midline is. And we know the amplitude is 2, so the highest point would be 3. -5 plus 2 is 3. And then -5 minus 2 would be -7. So that's sort of why I chose those numbers. Okay, so let's go back to our screen, and we'll just finish off with some notes here. So the d value tells us, they call it the vertical displacement. But what I think is more important is it actually tells you where the midline is. And the midline will always be at y equals d. So let's give you a question that has an a value and a d value, and sort of show you how you could graph this pretty quickly and answer like a whole bunch of questions from it. Make it a pretty big vertical displacement here. So once again, someone says, well, I want you to draw what this looks like, or tell me what the maximum or minimum of the graph is. And so I always just draw this like it's like a drunken T. This T falls down on its side, and you're going to have a high point, you're going to have a midpoint, and then a low point. I have lots of low points in my life. Anyway, here we go. So here's our T. We've got our 4 quadrants. We've got our high point, midpoint, low point. And now I need to draw things here. So once again, I would stay clear of putting any numbers on this picture right now. And I would draw what a cos graph is supposed to look like. But remember, it's a positive cos. There's a positive in front of here. There's no negative, so positive 3. So the cos should not be flipped. So where does cos start? Well, cos always starts up high. And then it goes to midpoint, and then to low point, and then to midpoint, and then to high point. So you get this cup shape here. Cos always kind of looks like a cup. And of course, if you have a negative cos, it would be flipped. And so now what I would do is I would put my numbers on the graph now. And you can start with any axis you want. I'm going to start with the x-axis because I haven't changed the period of the function. So that's going to be 2 pi. That's going to be pi over 2. And then 3 pi over 2. So that's that part. Now, if you're going to start labeling these things, what I probably would do, is encourage you to do, is find things like amplitude, find things like period. We haven't really told you how to do that yet. I would find the midline. And there's a 4th thing called phase shift, which we're not going to do today. So my amplitude, well, that's my A value. So what's the A value here? Well, it's 3. So the amplitude is 3. And the midline, that's the D value, and that's 7. Okay. Now you could get questions like what's the maximum? What's the minimum? And we'll show you how to answer those just from looking at the equation. But I'm going to sketch this because I always think it's easier for people to see it from a picture than it is from just writing notes here. So the midline is the first thing you should really find on your graph. That's the first thing we should look for. So this line right here should be 7 right here, because that's where the midline is supposed to be, and that's the middle of the graph. It's been moved up 7. And then the amplitude is 3. So from the midline to the highest point is the amplitude. So this is supposed to be the amplitude of the function. So if the amplitude is 3 and you're starting at 7, well, then your highest value would be 10. And of course, if your amplitude is 3, the lowest value should be 7 minus 3, which is 4. So the maximum value would be 10, and the minimum value would be 4. Okay, so why don't we give you one more question of this type to do, and then we'll sort of start wrapping it up and just start checking the time here. So let's take a look at y equals -2 sine theta. Let's go minus 10. So look, you guys to sketch one curve of that. So basically draw one picture of what that would look like. I'll give you maybe a minute just to sort of set it up here. Okay, so what's our amplitude here? What's the midline? Okay, well, the amplitude, well, the A value is -2, but the amplitude is always the absolute value of A, so the absolute value of -2, so the amplitude should be 2. And the midline is a D value of -10, so we should have a midline at y equals -10. And then once again, I haven't talked too much about period yet, so I've just kind of been saying it's 2 pi, but not explaining why it's 2 pi. But let's take a peek here. So once again, draw your drunken T. And 1, 2, 3, 1, 2, 3, and don't forget your 4 quadrants. It's not very well spaced there, but you get the idea. Okay, so it's a negative sign. So where does sign start, first of all? Does it start high, mid, or low? So this is where you kind of need to know your your two curves. So which one of those is the sine curve? Well, that's the sine curve right there, okay? So sine always starts on your midline and then usually goes up, but in this case it's negative, so it should have reflected. So it's going to start on the midline, go to a low point, go to a midline, go to a high point, and go back to the midline. And once again, I'm not putting any numbers on my graph right now. I'm just showing a flipped sine graph. And now you should find your midline, which would be -10, -10 there. Let's move down 10. And your amplitude is 2. So if you go from -10 and you add 2, that would be -8. And if you subtract 2, you should be at -12. And then you have a period of 2 pi. So that's what you would get there for your picture. Okay, so I think I have time just to finish this off here. So hang in there for one more sec here, okay? So the last thing I'll take a look at is y equals sine of 2 theta. So we're putting a number inside the function itself here, which is what we call the b value, if you look at the initial statement above here. So I'm going to draw a little line. And what I'm going to do here is give you a sort of a question to think about, sine 2 theta. And let's say we make theta a certain number here. So let's make theta equal to pi. Okay, so we're going to say let's make theta equal to pi. Okay, so if I plug this in, I'm going to get sine of 2 times pi. Okay, and the sine of 2 pi, if you go back to your unit circle, 2 pi would be over here, and that's 1, 0, so that should be 0. And what if you made theta equal to pi over 2? So you're on the graph at pi over 2. Well, you plug that in, you're going to get sine of 2 times pi over 2, which is sine of pi. And sine of pi would be over here, and that's also 0, y value over r value. Okay, so it's not terribly helpful. What if we made theta equal to pi over 4, though? So you're kind of in between here. So this would be the sine of 2 times pi over 4, which is really the sine of pi over 2. And the sine of pi over 2 is up here, and that's 0, 1. So this actually will give us enough information to make some kind of sense of what this thing actually looks like. So if I draw my graph here, I'm going to go 1, 2, 1, 2, 3, 4. And I'm going to draw the original sine graph, just what a sine graph looks like. So you kind of get a sine graph like this. And this is pi, 2 pi, 3 pi over 2, and pi over 2. And I'm going to use my green graph to try to make sense of these numbers here. And I'm going to use Desmos to really confirm this for you guys. This might be a bit more algebraic, so that might not make as much sense. But if I go to pi, I should have a value of 0. So it should be at 0 here. So that seems to be the same thing really to me. But if I go to pi over 2, I should also have a value of 0. So pi over 2, I should be at 0. So it's really kind of bizarre looking right now. But if you go to pi over 4, that's 45 degrees, which would be in that area there. And notice you're actually at 1 now. So you actually would be here. And if you graph this thing, what you get is this picture. If you're plugging more numbers in, you get this kind of graph here. So if you compare the black graph to the green graph, it looks like we've compressed it actually. We've altered the shape itself. So let's just go one more time back to our Desmos here. And let's just take a look at doing that. And I won't write on this screen because I'm sure you guys are getting exhausted of me writing stuff. But let's take a look at our first equation. So let's say you were graphing y equals just simple sine x. And I'm going to change my screen here to, let's go y values of -1 to 1. And my x value, let's go from 0 to 2 pi. And let's just graph that. So there's my sine graph. So typical sine graph starts in the midline, goes up, and then back down, and back to the beginning again. Now, if I go to enter a second equation, I go y equals, now not 2 sine x, but sine 2x. So notice the number falls within there. Then you get this. And you can actually see, I'll trace this for you guys, you actually get 1 and then 2 periods now. So you actually see the sine graph twice. So having a 2 there gives you 2 periods between 0 and 360. But more importantly, it gives you a compression of the graph. So the period's different now. So for example, the red graph went from here all the way to 2 pi, but the blue graph, it repeats its pattern after pi. And in fact, you can actually do something I think interesting here. If you go y equals sine bx, and you can actually create a slider bar here. And so right now the green graph has a b value of 1. And so you can see if I make it 2.3, and it's just creating more and more and more and more compressed waves here. And so you can make it whatever number you want. But notice when I go from about 1, oopsie, come on, go to 1, come on, come on. There we go. I'm at 1. So notice when I'm at 1, I get my normal sine graph. But if I make the b values bigger than 1, you actually see more pictures. Sounds kind of weird. You make the b value bigger, you get more and more pictures here. And if you make it smaller, you really get weird kind of reflection kind of thing. So we're going to deal with b values that are always positive numbers. So basically, you're going to be like 2s and 3s and stuff, and that actually causes a vertical compression or expansion. So I'm gonna flip back here, and so it'll be the last little bit of notes here. You guys survived a massive day. Let's go back to here. So let's take a look at a b value. So I'm going to go back to, well, I guess if someone said, what's the period of this function? It's pi. But let's give you a more basic definition. If you have y equals sine bx, or y equals cos bx, the period of these functions are always equal to 360 degrees divided by b. They usually in the book put absolute value of b here, but I won't be giving you any negative numbers, so it won't really make a difference if you don't put that in. And then another way of looking at it is 2 pi over the b value. So here's our last question, and we'll draw the whole thing out here. Okay, so let's try this. Y equals negative 2 cosine 3x plus 1. And what I'd like you guys to do is see if you can tell me what the amplitude would be, what the period would be, and where is this mysterious midline. So take a minute just to see if you can solve those things there. I'm just going to crack open a beer here. Yes, it's actually a 7-Up, but I have been doing a lot of drinking of pop. So, and here we go. So okay, so the amplitude has to do with the a value. The a value is -2, so the absolute value of -2 is 2. The midline is the d value, and the d value is 1. So it should be y equals 1. And my period now, so that's kind of new. Now I'm going to work in radians here because that's pretty much what math 12 is about. So basically I'm doing 2 pi over b. And my b value is 3. So my period would be 2 pi over 3, which is the same as 360 over 3, which is 180 degrees, I believe. 120 degrees, actually, 120 degrees. Okay, so what do we do? How do we draw this? Like we can get that just by looking at the formula. In fact, what do you think the max would be? And the min would be? Because you can actually do that without using the graph to interpret it. And how you do that is you look at the midline, you say, well, I'm at 1, and my amplitude is 2. So basically from 1, you go up 2, which gives you 3. And if you go from 1 down 2, that would give you -1. But let's use the graph to confirm that. Okay, so I'm going to draw my cosine graph here. But do I do a flipped cos or a normal cos? Well, let's look at the beginning. It's negative. Well, that means we flipped it. So cos should start normally high, and goes high, mid, low, mid, high. But we flip it, and so now we start low, and then we go mid, then we go high, and then we go mid, then we go low. And once again, I'm not putting any numbers on when I do that. I just draw an inverted cos. And now what I want to do is do the numbers here. So the first thing we should do is the midline. So the midline's at 1. And then my amplitude is 2. So I go up 2, which makes that 3. So that's why the max is 3. And I go down 2, which is -1, which is why the minimum is -1. Now, what can be hard is the next part here is putting the numbers on the x-axis. And we have to understand what the period is. So the period we said was 2 pi over 3. So 2 pi divided by the b value. And now notice that you have 4 quadrants. So basically every quadrant is going to be a quarter of the period. So you got to be somewhat savvy with your fractional math here. So 2 pi over 3 times a quarter would be cancel the 2 into the 4, So it's going to give me pi over 6. Or if you did multiply it out, it would be 2 pi over 12, which is still pi over 6. So basically, this first number is pi over 6. The second number would be 2 pi over 6, and then 3 pi over 6, and then 4 pi over, hi Evan, over 6. That's my son. And if I reduce those, this would be pi over 3, and this would be pi over 2, and this would be 2 pi over 3, which, notice, that is the period of the function. But I think that can be quite tricky. So I might do a bit more of that in another video, but you guys have lasted a long time. So I'm going to switch back to the sort of the view screen. If you want to show me your faces again, you're more than welcome to. It's always nice to see you guys. And we will wrap it up here. So does anyone have any questions at all or concerns? Might have put you all to sleep, so no one's unmiking, no?
When will we get to know what we did wrong on our logs test?
Oh, yeah, did you do the second one or the first one?
I think I did the first one.
Okay, I've marked one of them, so I'll have to check what that is. And when you get it back, you should be able to, if you click on the assignment, you should be able to see that I've done marking on it, and it will show you which questions you got wrong. And I plan to send out the logs test tonight, and then tomorrow to send out the sequences and series test.
Okay.
Okay, so look for the logs test tonight, and then the sequence and series should be tomorrow.
All right.
Okay, and for those of you who join, we do have a quiz tomorrow, and there'll be some homework tonight and some homework on Thursday, and then you'll hand in a small amount of homework over the weekend. Okay, so I'll say bye. Hope you guys are doing well, and we'll talk to you soon. Okay, see you guys.
See, Daddy.
Hey,